Hello, grade nines, and welcome to your lesson on compounds. We're going to be working on different types of compounds, learning how to write the formulas and the names. And oh, there's so much good stuff in this lesson. So here are our learning objectives for today. You are learning how to explain the difference between ionic and molecular compounds. So how you will know that you have had success is if you can explain the different bonds that ionic and molecular compounds have or make inside of them. If you can give two identifying factors that distinguish between ionic and molecular. So how do you know which one is which? And then you can name an ionic compound using the following steps. And we're going to go through that as we go. So compounds. First of all, in chemistry, our terminology is incredibly important of what do I mean when I say the word compound. And a compound is when we have two or more different elements bonded together in definite proportions. So, for example, this is water, right? H2O. I've got two H's and one O connected. In CO2, carbon dioxide, I have two O's and one carbon. The big thing here is that they are chemically bonded together. We're going to talk about the bonds that we actually have. But this is different than if we had a mixture. In a mixture, it's not actually bonded together. It would be instead two separate things that each still retain their chemical and physical properties. So I like talking about this really quickly. If I had, for example, H2 gas, okay, and that's hydrogen, and O2 gas, oxygen, if I had a mixture of these two things, it would be explosive. Hydrogen actually combusts very quickly in the presence of oxygen. So if I were to light a match, kaboom, it would be a big explosion, which actually would result in making water. But hydrogen and oxygen separate are not the same as water made of hydrogen and oxygen in a compound. And the reason why it's not the same is because in water, those elements are chemically bonded together. So again, today we're talking about compounds where we have more than one element that is chemically bonded together. All right, continuing on. And I have to erase that mark and move my face up because that's not going to work how I have it. Oh, this is not smooth. Stick with me here. Stick with me. Yep, up, up. Oh, there we go. Okay, so moving forward. So definite proportions, basically, whenever I take a look at a compound, it's always going to be the same ratio between the elements in the compound. So for example, if I look at CO2, it's always going to be one carbon to two oxygen. This is the law of definite composition, that I always have the exact same ratio of one element to another element within a given compound. Now, if I had a different compound, like for example, if I had carbon monoxide instead of CO2, well, then that is a different ratio. And that means it's actually a completely different substance, right? This would be one carbon to one oxygen. So it would be a 1-to-1 ratio. But that's a different compound entirely. And what we're dealing with today is taking a look at these different compounds and then trying to figure out how to name and do stuff with them. So we're going to talk about two different types of compounds, ionic and molecular. This goes back to our periodic table in understanding the difference between the two. So in ionic, I have a metal and a non-metal. So just a reminder that when I'm talking about metal, this is to the left of the staircase line, excluding hydrogen. So I have something to the left of the staircase line, and then I have something to the right of the staircase line with the non-metal. So the classic example for ionic is sodium chloride. Sodium is a metal, and then chlorine is a non-metal. Now, when I put these two elements together and they chemically combine and react, I end up getting an ionic compound where electrons are transferred from one element to the other element. What actually happens here is that sodium ends up giving an electron to chlorine. And as we actually dealt with in Bohr diagrams, that basically ends up giving it a stable octet, meaning a full outer energy level. So I'm actually going to go ahead and draw some diagrams here, but I'm going to use slightly different elements because it will make for an easier example to show. Let's say that I had lithium and fluorine. So lithium has 3 protons and 4 neutrons in the nucleus, and then I would have 2 electrons right here. Then I would have a third electron right here. Oh, and that's relatively messy, but it's tough with this pen. And then if I take a look at fluorine, I would have 9 protons, 10 neutrons, and I have 2 electrons in the first ring, and then I have 7 electrons in the second ring. 1, 2, 3, 4, 5, 6, 7. So that would be the Bohr diagram for fluorine. When lithium and fluorine actually combine, what takes place is lithium, if it loses this one electron, gets a full octet because the ring underneath it has 2 electrons, and that's the max amount of electrons the first ring can hold. So atoms become most stable when their outer ring of electrons is full. Another way of saying that is they have a full valence energy level. By losing this one electron, lithium can have that full valence energy level. So it loses that one electron by giving it actually to fluorine. Fluorine had 1, 2, 3, 4, 5, 6, 7 electrons. By gaining one, it gets 8, which gives it a full outer ring. So that actually would make fluorine stable. So when I have an ionic compound, what happens is electrons are transferred from one thing to another thing in order to get those full outer rings to make those atoms stable. When that happens, they become what's called ions. Ions are essentially atoms that have an uneven amount of protons and electrons, meaning they have a charge. For this lithium, if I'm losing that one electron, it now has a positive 1 charge because it has 1 more positive protons at 3 than negative electrons at 2. So it has a 1 positive charge. Now, fluorine ends up gaining an electron, so it's going to have a charge of 1 minus because it has 9 protons and now 10 negative electrons. So it has a 1 negative charge. Because we now have these opposite charges between lithium and fluoride, lithium ion and fluoride ion, they attract because opposite charges attract. So by doing that transfer of electrons, I now have 2 ions that are attracted to each other because of their opposite charge. So what will I observe for ionic compounds? What are some properties that I would see? Well, one thing is that it conducts in solution. This word of solution is so important. What that means is that it is in water. It is not going to conduct unless it actually is in water. Another thing that we can actually add to this, oh, it's right here, is that most ionic compounds dissolve in water. So if I put an ionic compound in water, it typically will actually dissolve, meaning you won't be able to see it anymore because it has broken up into such incredibly tiny pieces that it's no longer visible to the eye. Another thing that's kind of neat is that ionic compounds make this repeating 3D pattern that we call a crystal lattice. So because I have these positive ions, with the example I gave, lithium is the positive ion, and these negative ions that are attracting, they repeat each other over and over and over in 3 dimensions. So I kind of like imagine like a checkerboard where one color, like red, is positive and then the black is negative. And essentially what happens is we get this repeating checkerboard pattern because we have positive ions and negative ions trying to get as close to each other as they can, attracting in 3 dimensions. Okay, so that is what a crystal lattice is. It's a regular repeating pattern of these positive and negative ions getting close together. Okay, for molecular, it's totally different. So now what I have is a non-metal and a non-metal. So looking at that staircase line again, I have to the right and to the right. So 2 non-metals are binding together. Unlike what we had with ionic, it is not a transfer. Instead, electrons are shared. So what happens is electrons end up actually being shared between the 2 atoms in order to, again, get that full octet, to get stability. Okay, so I'm going to show you a quick example of how this would work. And probably one of the easiest examples would be water, which is also a very famous one, right? That we've already talked about a bit. So in water, I have H2O. So I have 1 oxygen atom. And that oxygen atom has 2 electrons in the first ring, and then 6 electrons in the next ring. 1, 2, 3, 4, 5, 6. So I have 8 electrons total, right? 2 in the first ring, 6 in the second ring. So this is good review of actually just how to do Bohr diagrams. Now, when I take a look at hydrogen, I'm going to draw it up here first. It only has 1 proton in the nucleus, and then it has 1 electron, okay, outside of that. So now here's what can happen. Hydrogen has 1 electron right now in its outer ring. It needs 1 more to get to 2, which is the max the first energy level can hold. So what we can do is we can actually pair up this electron with this one, and then that makes a stable octet, a full outer ring for hydrogen. So I'm going to redraw my hydrogen right here, very messily apparently, where I have 1 proton, and then here's the 1 electron that came from hydrogen. Now hydrogen, by sharing this pair with oxygen, has its full outer ring. Its first energy level now has the 2, which is the max it can hold. So hydrogen is now more stable. If I take a look at this side, I can do the same thing with the second hydrogen. So here is my second hydrogen, which has 1 proton. Now this has a full outer ring for hydrogen as well with its 2 electrons. Now what's neat is oxygen now also has a full outer ring. By sharing these 2 pairs of electrons with the 2 hydrogens, it now has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer ring. So by sharing electrons, which we call a covalent bonds, by sharing electrons, it gets those full outer rings. Covalent is actually kind of a neat term. You think about co, like meaning more than one, and then valent being like valence energy levels. So I have valence energy levels working together in order to share electrons to make this bond. I should have said that in ionic, I have what's called ionic bonds. So by transferring the electrons and having oppositely charged ions, that's called an ionic bond, the attraction between those ions. So molecular, I have sharing of electrons, that is a covalent bond. In terms of properties, molecular compounds do not conduct in solution. Okay, they don't conduct outside of solution either, but they don't conduct if we put them in water. They have distinct molecules, so it's not a regular repeating pattern like we have with ionic compound. And H2O is literally 2 H's and 1 O. And all the molecules of water are separate from the other molecules of water. Most ionic compounds are insoluble in water, meaning they do not dissolve. And then also, most molecular compounds have a low melting point. They have a low melting point compared to ionic, which has a high melting and boiling point. That's what this means. The PT means point. So all ionic compounds are actually solid at room temperature. Well, when I take a look at molecular, it would be solid, liquid, or gas. Could be any of those states at room temperature. Okay, so molecular compounds, they don't take as much energy to actually melt them, to boil them, as ionic compounds do. There's always exceptions to this, but that's kind of the empirical properties for that. Okay, so moving on, I'm going to have to end this video soon and make a new one, just in terms of how much time this one itself is going to take up. So let's take a look at these 4 and figure out, is this ionic or molecular? Now, I'm actually just going to quickly back out of this presentation view because I don't love how this is showing up for subscripts. So I'm going to go ahead and make that a small 4 and this a small 2, which is what it would be for a proper formula. Also, we'll talk about in a minute the fact that these are actually missing states, which is something that we want to get really good at Science 9 because it's critical in Science 10 that we can do states. Now I know I disappeared here, just give me 1 second and I'm back. Okay, so if we take a look at these and try to figure out if it's ionic or molecular, the big thing you're asking yourself is, does it have a metal or not? Right? If it has a metal present in the formula, a metal element, then that means it's ionic. If it does not have a metal, then that means that it's molecular. Okay, so molecular has no metals in them. I don't know why I put the question mark. That can actually just be exclamation mark. Has a metal. It's ionic. Does not. It's molecular. So take a quick look at your periodic table and see, does this have a metal or not? I'm going to actually, well, stop. You should pause the video, try it out, and then come back and I'll tell you what the answers are. Okay, so here are the answers. If I take a look at sodium iodide, that has a metal in it. Sodium is a metal. So, oh, the reveal? That doesn't work. Whoa, we just changed screens. Okay, I'm going to go back to pen. That's going to be the better way of doing this because I can't move the objects in the mode I'm in. This is ionic because sodium itself is a metal. So that is a metal element. Now, given that it's ionic, I actually know what the state is because all ionic compounds at room temperature are a solid. So I can actually put a little bracket there, an S, and then another bracket. And that's how I show the state on a formula. CH4, it's all nonmetals. So this is actually molecular. Molecular. This is natural gas. This is methane. And it's molecular, so I know that it could be a solid, a liquid, or a gas. This being natural gas is actually a gas. This is what goes into your furnaces. It's what you let out when you fart. This is methane gas. And then finally, water. You know water. You know water. It's a liquid, of course, at room temperature. And this is molecular again because of the fact that it is all non-metals. Okay, that was one slide. We can actually do this again on the next slide as well. So yeah, again, maybe you just pause it for a second here. We'll come back and we'll identify what it is. Pause. Okay, here are the answers. Sodium chloride. Sodium, again, it's a metal. So this is going to be ionic, right? Because it has the metal in it. Carbon monoxide is molecular. And then magnesium oxide, magnesium again is a metal, so this is going to be ionic. So given that sodium chloride is ionic, it's going to be a solid. Carbon monoxide being molecular, well, that's going to be a gas. And then MgO being ionic, that's going to be a solid. Now, molecular doesn't have to be a gas, right? It could be solid, liquid, or gas, but carbon monoxide is actually what we worry about with carbon monoxide poisoning. It's the reason why we have carbon monoxide detectors. So we actually know that's a gas just from life. Carbon monoxide, really interesting. It actually binds to the hemoglobin in your blood. So your hemoglobin can't actually bond to oxygen, can't carry oxygen throughout your body. So it essentially ties up your hemoglobin in your blood that would normally carry oxygen, so you can't. So incredibly dangerous, right? And lethal. And then, yeah, magnesium oxide ionic. So at the end of the day, you look for that metal. I kind of think ionic is kind of like this like metally term, right? I think ionic, it's like technology, metal type stuff. So that's maybe how you want to think about it. Well, molecular is more soft. So that's your non-metals, right? Molecular is non-metals. Because we know that non-metals are solid, liquid, or gas. They're not, hard, or as hard as like a metal is. So we more think like, it's non-metal, soft, molecular. I don't know if that helps. You could think about moles. Moles are fuzzy and soft. Yeah, okay. And I'm talking about the animal, not the skin blemish. So I think looking at what the next slide is, give me 1 second here, then I'm probably going to end this here and split into another video. No, we got one more set of these. But again, it's just kind of ugly for the actual how this looks. So let's change this to, again, a subscript. This will again be, oh, there's kind of a rogue thing there. Sorry, should have totally done this before the video started, but now I'm too far in to start it again. All right, got a fun little extra neat font on there as well. Okay, so going back in here, oh, and I'm back. Okay, so CCl4, AlO3, and NH3. Take a minute, think about it, come back, maybe try even without your periodic table, see if you have any success. Okay, and here are the answers. For CCl4, this is molecular because it's all nonmetals. AlO3, aluminum, is a metal, so this is going to be ionic. And then NH3 is all nonmetals again, so I have molecular. Okay, so these are the types of compounds we're having. So molecular has covalent bonds in them. They're sharing electrons. Well, ionic has ions in it, ionic bonds. There is a transfer of electrons there. Okay, so that's it for this quick lesson. Spend some time studying over ionic and molecular properties, the differences, what different elements are involved. Super important we understand that before we go into the naming and the formulas, which is the next step and we'll be dealing with in the next lesson. All right, bye for now.